Hi everyone. My name is Sidney Henley. I'm a machine learning engineer at Oregon National Laboratory, and I'm going to show our work about global compute related to our federated learning framework. So first, a quick introduction about what is federated learning. In federated learning, there is a central server, and there are several clients. They have their own computing machine and their own local data set, and they consider their local data sets as private, containing some confidential and security data. So they don't want to share those data, but they want to train model using those data. The problem is that their data may be biased or limited. So they want to collaborate with others to train a more robust and generalized and better model without sharing their sensitive local data. So to achieve that, they train model on their local data and share the model parameters to a central server. The parameter kind of aggregates those model parameters and back for further local training again and again until reach some stopping condition. And in terms of like implementation or execution, there are two communication patterns. One is client-driven and one is server-driven. So client-driven, it is an example is implemented using a gRPC, where we have a server and several clients. The clients first perform local training using their local data and get a model. And then it sends requests to the server, say, hey, I want you to perform some global aggregation for my model. And then the server perform that global aggregation and send the results back. So in this case, it's called client-driven because the client send the request for the server to initiate the aggregation. Well, for server-driven communication, which can be realized using global compute, the server will send local training tasks to the client machine. Say, I want you to train your model for a certain number of steps, and then the client perform the local training, send the locally trained model, and then the server perform the global aggregation. So what is the difference and what are the benefits global compute or say server-driven communication can provide compared with client-driven or gRPC? The first one is that it enables simple experiment launching and testing. All the codes and configurations, they reside on the server side, making the experiment launching and especially code or configuration updating as easy as serial examples. Suppose that you want to update a piece of code. There's no need to email your client, say, please, run git pull to pull the new code, and then we can start writing. You can change everything on the server side just as serial experiments. And second is that it enables simple experiment coordination. So basically, there's no need for each client to sit on in front of their machine to run Python, run client.py, almost at the same time to send requests to the server. Now the server can just send global compute tasks to them, and then they can allocate resources to execute the task. So it makes the coordination easier, especially for international collaboration. There's no need, right? When people reside on different time zone, the coordination is easier. Third benefit is that as global compute is integrated with global auth, it provides robust identity and access management. And the fourth benefit is that it has no inbound connectivity requirements for both server and clients, because there's an intermediate global server helping us to transfer the task and results back. And this makes some HPC resources such as Polaris it can serve as the server. Otherwise, if you run the gRPC server on Polaris, it cannot accept inbound traffic, so it cannot work as a FL server. But with global compute, machines like Polaris can also serve as a federated learning server. And global compute also enables federated learning on heterogeneous clients. It can be different HPCs with different job schedulers. It can be the computing resources on the cloud. And when we did an experiment, I think a year ago, we find a problem. So we use one GPU machine on Azure, one machine's Polaris node, and two CPU nodes on NCSA Delta. We find that different different machines take a significantly different amount of time to finish their local training because the resources are different. And there are significant resource underutilization, especially for powerful client machines. So the more powerful you are, the more resources you are wasted. This is not fair. So here are some existing solution to resolve this is making the federated learning process asynchronous, which means that whenever you have a local model sent from clients, update immediately the global model. So there's no need to wait, but there's problem with that. So here's an example. Suppose we have two machines, client 1 and client 2. Client 2 is more powerful, and it takes about 15 minutes for client 2 to finish each local training round. And then we can see after each 15 minutes, client 2 finish local training to update the global model. So after 1 hour, the global model is updated for 4 times. It is at model version 4. And then after 1 hour and 5 minutes, client 1 finally finished its first local training job. But in this case, it is trained on model version 0, but the global server is already model version 4. So the local model, it is we call it stale or outdated compared to the global model. And as a result for that, such local model can be either detrimental to the global model if we aggregated it, or people usually apply a small importance weight to penalize that stale local model. But this may cause the global model to drift away from data on the slower clients. It is already slow and you apply a small importance factor. So this is too bad. So here's our solution. So we try to synchronize the arrival of clients' locally trained model by assigning a different number of training steps to them according to the computing power. But the problem is that in practice, the server does not know what is your computing power, and that may also change during the training process. So our solution is adding a computing power aware scheduler on the server side, which can estimate and update the computing power of each client on the fly, synchronize the arrival of a group of clients by assigning different number of tasks according to the estimated computing power, and then the scheduler will interact the server-side scheduler to update the global model. So here are some results. We can so basically you can see the top few lines are different variants of FedCompass. It can achieve much better converge accuracy than other asynchronous algorithms, and it converges faster than synchronous algorithms. And this plot also shows what is the resource utilization looks like for synchronous scheduler, Compass scheduler, and asynchronous scheduler. We can see Compass scheduler can also kind of fully utilize the computing resources. Well, asynchronous, even though it's almost fully utilized, it still cannot achieve good model performance due to the client drift problem we mentioned before. So here are some next steps for our federated learning research is that connect popular cloud providers for low-cost FL. So FL is important in medical applications where data privacy is paramount, is essential. And most hospitals have their private data on cloud storage, as well as their computing facilities on cloud as well. But training on cloud GPU instances can be costly. It's not cheap. AWS, Google, or Azure, they both provide something called spot computing instances, which is much lower price, but it can be queued at any time with a short notice. So we would like to add course-aware aspect to the computing-aware scheduler to reduce the cost for FL experiments among heterogeneous cloud computing providers using their spot instance and making the setup process as streamlined as possible. It takes care of fault tolerance things. Yeah. So here are some references. Here's the code for our framework. We also provide documentation with detailed tutorial on how to use it. And here are some reference paper we mentioned.